Well, g'day and kia ora and good morning, everybody, and welcome to Markham's latest online event. Today we're focusing on the topic of, does stronger concrete always mean longer lasting concrete? Just get to this screen sharing and introduce the team. Okay, with us today we've got Doug and Charles, who are based in our Napier office. An experienced team and can answer your questions as we go along. They'll introduce themselves as they come on board. The agenda for today is concrete strength and durability of the myth versus the reality, special needs of low carbon and green concretes, and how to specify for durability and not just strength. Doug, would you like to take us away and start from the point of what we mean by concrete strengths?
Yeah, sure thing. So thanks, Brendan. My name's Doug Hamlin. I work in the research and development section here at Markham. Been here for 14 and a half years. So yeah, been through many roles in the business, from application on site through to specification work with architects, engineers, construction sales, project management. Done a lot really, and yeah, I'm very passionate about long-lasting concrete durability, and so yeah, what we wanted to have a look at first was the what we actually mean by concrete strength. Now, there's as you can see there's a couple of main ones, the compressive and tensile. Firstly, we'll look at the compressive test. So that's compressive strength. So that's looking at the ability of the concrete to reduce, to withstand load. So that's load that's compressing down or pushing down on the concrete or onto the structure. And this is typically measured by loading up a concrete cylinder to the point that it fails. And that gives you a reading, MPA reading there, and then that's taken as the strength of the concrete that you're designing to, or that that's required for that structure. Now, tensile strength is essentially the other way around. So it's rather than looking at the pushing force, it's looking at the pulling force. So that concrete's ability to withstand being pulled apart or being being flexed, and how that's done is that same cylinder is put on a machine and pulled until the point that it breaks. And then that is known as the tensile strength there. So it's normally, say if you've got a 40 MPa compressive strength, your tensile strength's normally about 10% as a general rule of thumb of your compressive strength. Now, a couple of other items that have been looked at a lot more in recent times, especially with the green push or with the cement replacements. The early strengths is, your 1 to 3 days strengths is really becoming really important in construction now. So, if you think about being able to remove formwork on site, being able to carry on the construction program, being able to pull precast panels off the casting beds, that sort of thing. And so, yeah, it's something that's really, really measured now. And just lastly, on the unit of strength there, that is measured in megapascals, which is a calculation from the amount of load in newtons and the square millimeters of the concrete cylinder, the height, all those dimensions. That's all calculated, and you get given a MPa reading there for the strength. So if we could go on to the next one there, Brendan. So with compressive strength, it's really probably the most common factor that's used to when you're specifying and designing concrete. It's one of the key bits of information that is looked for when you're building a structure. And with that, a lot of the time it's used as kind of the indication or the sole factor to determine what a suitable concrete for the conditions that you're designing in. So if you say okay, we need it to be highly durable concrete. Let's go for as highest MPA as we can. But therein lies the problem in that it's not just the MPA or the higher the MPA doesn't mean higher durability in the concrete. So there's things like specific mix design. So you could be having a lower MPA concrete, say a 40 MPA concrete, with the right conditions, right mix design, that could actually outperform a higher MPA concrete. Now, this is not a complete blanket statement, but it's very true of many construction sites, because they're not taking into account, they're not doing a quality curing on site. They maybe not doing quality finishing. They're not, the long-term site environment is not being considered. And most importantly, the impermeability is not being considered. So you could have a 60 MPA concrete, gets poured on a bad weather day. You're resulting in a whole lot of drying shrinkage or plastic shrinkage, cracking, and that structure is much more susceptible to corrosion damage, to deterioration, than say a lower MPA concrete that's poured with right conditions, right admixtures, everything's been thought out there, and it's a quality concrete that you end up there. So yeah, I just really want to challenge that thought that you may have, that compressive strength is really the only measure of durability in concrete, because it really isn't. There's as we can see, there's 5 factors on the screen there. I'm sure there's more that need to be considered when you're looking at durability of concrete. I'll hand over to Charles now. He'll go diving into this a little bit deeper.
Yeah, thanks, Doug. Just before you start there, Charles, I'd just like to welcome those who have joined us since we started. Thank you very much. And down the bottom in your toolbar, or under the More tab, you'll find a questions button and a chat button. We really welcome your questions as you go along. We're going to have a Q&A session at the end. And if you have any suggestions or additions to what we're saying, please do drop them in the chat. We'll be happy to discuss. Thanks, Charles.
Awesome. Thanks, team. I'm Charles Curry, and I'm focused on precast and ready mix, helping a lot with ready mix to improve mixes, make them work better, especially responding to a lot of the changes we're seeing in the drive towards low carbon cement. I've been quite involved in projects since I've been here at Markham. A lot of existing concrete infrastructure, mining infrastructure, marine, bit of all sorts. So been up close with a lot of the attack and interesting things that it's subjected to over the course of its life. So just wanted to dive into this subject a little bit more. Some of the areas we're separating out durability from strength, where it can be specified, and yeah, so lowering the permeability, stopping the chlorides and water ingress is obviously a biggie. Obviously the corrosion needs these free needs the concrete to be permeable in order to progress. Upping the reinforcement cover, the protection of the rebar is a big way to protect the attack. Once that surface is broken down, the underneath is pretty much free for all in some cases. We're seeing a lot of SCMs, supplementary cementitious materials, being used now, such as fly ash, silica. A lot of these are improving the resistance of the pore structure to prevent attacks over the design life of the concrete, and responding to the environment that it's in. A lot of attack from soils, marine exposure, harsh conditions of mining concrete, for example. So just bearing that in mind in the design of the concrete, the actual environment that it's going to be in.
Yeah, that's good, Charles. I just want to just what you touched on the permeability there. That is really, really important when you're considering concrete. So we've seen concretes that were, up to 80 MPa even. I think it's the highest we've tested here for water permeability. We can still get moisture into that concrete even at that high MPa, and there's a bit of a belief out there that once you hit 40 MPa in the concrete, it's waterproof. It's not going to leak, and that's typically in the case of, say, a water reservoir or a water tank, something like that. Now, while that's not entirely untrue, that 40 MPa is going to withstand that. It's not going to let the water come through like a river. What you are forgetting there is that it is still getting through to the reinforcing steel over time. So it might be with holding that water in that tank, but it's not stopping the moisture getting through the concrete and it's starting and taking contaminants through to that reinforcing steel. So yeah, that's just something I wanted to highlight there.
Not to mention too that being the higher MPa, being more chance of cracking, and then it using those cracks to progress as well.
Yeah, that's right, exactly. Carry on there.
Yep, we'll go to the next slide. So yeah, couple of key ways that this is done. Performance-based specifications is more like a shift towards design life predictions. So yeah, once again, in targeting in these real world conditions needing to be met effectively. But do you want to share a few examples of what this looks like in the real world, Doug?
Yeah, I do. Yeah, so the with these low carbon cements, they do change in terms of, we've mentioned the early strengths. That's one area. They do change in terms of workability, water demand, things like that. So the old kind of to code prescriptive approach doesn't always work with these cements, and it's really important to, as designers, to specify the performance that you want over the design life. So you might be aiming for a 50-year or 100-year design life, and have like a chloride diffusion requirement in there, or a whatever test it may be, that ready-mix companies, construction professionals can come up with a mix that meets those requirements. So rather than just specifying a water cement ratio and a strength to meet, it's really important with these low carbon mixes to specify the performance requirements, because they simply just don't place and finish and work on site like your traditional concretes did. And it just makes it even more important to have that performance based specification there, rather than prescriptive.
Yeah, definitely. That's good. Yep. Yeah. So the other way is to obviously innovative additives for durability. The nanosilica hydrogel admixers will actually help improve the microstructure, and if, in short, making the concrete work as good as normal traditional concrete where these SCMs have been added. As Doug mentioned, there can be a lot of changes. So it's helping on both the short term and the long, like for placing, etc., and the longer term as well.
Thanks very much all for questions coming in. That's good. We'll address those a little bit later on.
Awesome. We'll head into a few project examples and get to them, eh? No,
Yeah.
not quite.
Yeah, that's good. So I mentioned the performance specifications there. So how do we actually specify that? So how do we specify for long-term durability? These are a few of the parameters that we have seen it been done very well. So looking at the permeability of the concrete, so specifying a depth and penetration of water under pressure. There's a standard test for that. The chloride diffusion, so looking at a number there, that's a lot of the actual roading authorities, particularly Transport for New South Wales does. The Queensland roads do as well, have a number there that they want you to target in a mix design, so that you have to come under that in any trial mixes. That's a very good way. Those two factors there are very easy to demonstrate in a test, and it doesn't take years. It more takes 1 to 2 months to show that the compliance to your performance requirement there. And what that also does is it gives you ready mix providers, gives you construction companies a bit of room to move, to adjust and optimize a mix design, because concrete is so variable from even different states within Australia, different quarries, the weather. There's so many things that go into a concrete mix, and it's if you can give it a performance requirement for someone to meet, using their local knowledge and the materials that they're working with, it's just you just get that lot better result, rather than just prescribing a set number of mix requirements. Some other areas we do see not as common as the resistivity. So that's using a device that measures the resistance to electrical current through the concrete. There's there's not many, but there's a few suppliers out there now with the devices for this, and that measures the inferred ability of the concrete to resist moisture transmission, resist chlorides through the concrete, and also give you an indication of the corrosion potential of the rebar. So that can be included as well, so a level there. The VPV is probably more of a traditional approach, used by Vic roads, WA roads, and what that does is give you a level of voids, or a percentage of voids in the concrete that the concrete needs to hit. It's not an ideal test, specifically when you're talking about low carbon concretes, but it is quite a fast way to make sure a concrete is compliant and it is hitting requirements there. So yeah, it's something to look at there. And lastly, I almost feel like this is one of the most important points, from the point of view that it never, not sure, I shouldn't say never, it really happens on site, and that is where a contractor actually follows the the curing specification. So as an engineer, you may put in that it has a 3-day water cure, or a curing membrane, or a curing treatment equal to water curing, but to ensure that actually happens on site is very important. I think the figures are something like you can lose up to 50% of the durability of that concrete if you don't cure it properly. So you could have done everything else right, and then it goes on site and it's not, that moisture loss, that curing isn't controlled after it's been poured, and you've just undone a whole lot of great work there. So yeah, I'd really stress that's included in your checks on site, that type of thing, that it is included, and monitor it for the first couple of pours, make sure it is actually happening there.
Often can fall down the cracks a bit, no pun intended, and even just where there's not something specified, it just kind of becomes a bit of a blame game. No one wants to pay for it on site, so
yeah, definitely. But at the same time, it is a contracted thing. It is in the specification. So there's a sort of a reason, a mandate to follow that up there.
Definitely.
Right. So just want to have a look at a few projects now. So looking at what we're talking about in the real world, how Markham has actually helped these projects. So first one goes back to early 2000s. The structure, not sure exactly how old it was, but it had some severe corrosion, wasn't supporting its own weight, and this concrete was actually trucked from Gisborne up to Tolaga Bay, which I think the travel times varied from between 4 and 6 hours. By the time the last bit of concrete was being discharged, and that was wheelbarrowed out along the wharf. It wasn't strong enough to support the truck, and it was placed down the shutters. And what was interesting about this was predominantly to protect the concrete from the chlorides there. That was a hydrogel admixture, but it also worked with the concrete itself. So the requirement to travel for 4 hours and then be on site mixing for another 1 to 2 hours is very challenging to achieve, and that's something else to consider, is that workability of the concrete on site, getting that that quality finish, quality consolidation, that type of thing. Does have an impact on that long-term durability. So yeah, that's performing very well. One of our contractors went back there just in the last year, took that photo down on the right there, so you can see there's no corrosion evident that there, and we're coming up 25 years. So yeah, that's a good testament really to that durability being thought about right from right at the very start, and a successful result. Charles, I'll let you take the next one. Oh, no, this one's me. Sorry. So Carapatina, this is a mine site in South Australia. Very, very humid, hot conditions. They can get it tropical there, can get it very, very humid, and then it can be very dry, so pretty harsh that way. And then the groundwater that they're using is also hypersaline. So all the washdown water can be up to 7 times the salinity of seawater. So you can imagine what that does to the concrete. It not only permeates through the concrete and attacks the reinforcing steel, but because it's so strong, it actually attacks the surface of the concrete as well. And they get degradation within 5 years there. So this is a perfect example of looking at the environment, looking at the conditions that a structure is going to be in, and designing for that. Now, this particular site, they used an admixture in the concrete that they're always using a traditional admixture, but they were having real problems with the workability and set times of it. So they switched across to a hydrogel admixture, which is neutral on set times, and did essentially the same waterproofing job, but because you could get a better quality result, or pour, the finishes, preferred placing it, everything like that, we're seeing a lot longer service life coming out of that environment than what they were using. And then coupled with that, they had very strict curing regime as well. So it was using a curing membrane, and ensuring that all that concrete was protected over that's early life. So yeah, that's a good success story there. Again, make it something that actually works with what your contractor's doing, and meets a performance requirement set by the client there. I think that's all to say on that one. Over to you, Charles.
Next one, the Ports of Auckland car park. We got involved. It was added extra durability was specified for this one. So obviously the normal attack of mechanisms for a car park, the carbonation from the exhaust fumes, the contamination brought by the tyres, and the constant wear and tear. But what was extra significance about this one was the exposed marine zone that it was in, the sea right there. So this was a good example of something that was extra work was put into, and yeah, so far so good.
Yeah, that's good. Sorry, Brendan.
No, just what I was going to say. Did you want to mention the wharf it was built on, or built adjacent to, which we had also worked on some years before?
Leaderslow Wharf.
Yeah, go for
Probably
it.
more intelligent on that than me. The one that was like the remediation.
Yes, one of our very early projects.
Yeah, that's obviously adjacent to the Leaderslow Wharf that we got involved in the early 2000s. There had been a lot of corrosion and damage over the years. It was actually right at the end of its design life, and it was one of the first large wharves that Markham got involved in, and there was significant repairs done, a lot of spalling, and then what we did was protect the areas around those repairs. from further breakout and contamination, and that worked really well. Going in, it was about 8-9 years later, there was no further corrosion and breakout from, this is the underneath of the wharf. So that was pretty awesome. Move on to the Manawatu Gorge Highway, really known as Te Ahua Turanga. This is a recent project we're involved in, the bridge superstructure. There's quite a bit going on there, but one of the main reasons we got involved with a durability admix was for workability. There was a microsilica content, I think it was about 8% off the top of my head, and number of challenges with this, namely the stickiness of the mix, which they did like a large site, like a pre-trial on site, pouring hollow core beams, and that went really well on a workability, on the side of workability. The advantage for the long term is that obviously this is a real significant asset as part of the new highway, and with making that concrete impermeable, they get the advantages of that long term durability. Yeah. Is there anything else you wanted to
that's
add
good.
to
Yeah, just to reinforce that, the hollow core molds that they were pouring, they needed to have that microsilica in there to meet the durability requirements of the code, but also have it workable, but not too flowable or workable that it put too much pressure and actually broke the mold there. So with the hydrogels, they really excel at, the official term is thixotropic, which basically means that it has very good workability when energy is applied to it. So while it's being vibrated, while it's being pumped in, it has, it flows around the rebar and everything nicely. And as soon as you stop applying that energy, it sets up and doesn't keep putting that pressure on the molds there. So yeah, that was again really an example of not just achieving high durability in the concrete, but actually working with the site conditions and what the challenges they had there.
That's awesome.
So yeah, that brings us to the questions, Brendan.
Yeah, that's really good. Really appreciate what you've gone through there. And we've got a question on the chat from Peter. When is galvanised rebar used? I have seen it, but it is rare. Did you want to have a bit of a talk about that? Galvanised and other forms too.
Yeah, that's a good topic. It does come up from time to time. I'd agree. It's not common. It's rare. And yeah, again, it depends on the site conditions. I guess the thing to consider is it's only as good as that the care that's taken while it's being placed. So if you get a pinhole or a abrasion on that rebar, and you break down that protective layer, you're through to the steel anyway. And it only takes one of those sites to start that corrosion process happening. Now, what I would say there is it's just as important if you're using galvanized rebar or epoxy coated rebar to still protect that concrete or still pay attention to the mix design of that concrete, and the curing, everything that's involved there. It's definitely not a get out of jail free card, and it's and it does come at cost. So it's worth, if you're going to do that, go to those levels, it's worth spending time on the actual concrete mix itself, including an admixture in there if it's needed, or making sure that the curing, everything is happening on site to achieve that long-term durability.
Yep, that's good. Thank you. That covers the question. And just be free, everybody, to drop your question or comments into the chat, questions in the chat. Love to hear from you. One other thing that crossed my mind, Doug, just while we're on this section, is you mentioned a number of things to specify on site, or for the durability as opposed to the strength. Is there something that you can look for on site fairly readily as to if you're doing trials or tests? What would you particularly look for?
Yeah, that's a good point. So yeah, we ran through a few of the examples there, but I really feel that specifying number one would be the chloride diffusion of the concrete. It not only tells you the resistance to chlorides in the concrete, but it gives you an indication of the permeability as well. So yeah, that would be my number one, and that can be done. There's a couple of different versions of the test. The shorter one is done at 28 days old and is finished inside 2 days. So yeah, it's not a long, when you're talking about a big project construction timeline, it doesn't take a long time to conduct that test. And then the diffusion one is more like 2 months before you get the results there. But yeah, that chloride permeability, I guess you'd call it. And there's some really good guidance in the B80 specification. Some of the other, I just can't remember off the top of my head, but we can get them out later. Where they've set limits for 100-year or 50-year design life, and what diffusion limit that you should be hitting, and that can be demonstrated by the ready mix plant there. Another area is water permeability. So there is on-site testing that can be done, as well as laboratory testing. Doesn't take long to do, and you can set a level there that you want the concrete to meet. But yeah, I would say first and foremost is to get that chloride diffusion, chloride permeability testing into your specifications. And then yeah, I mean, from there you can kind of build your framework there. But is that
as well as the curing? Yeah?
Yes, yeah. So the curing's is important. That's something you need to ensure happens on site. Because if you run a laboratory test for chloride diffusion, that's a water cured sample. It gets given a good life, so to speak. So if you're wanting to repeat that same process on site, you really want to make sure that the concrete's getting the best cure it can on site as well. If that makes
100%.
sense.
Yeah, it's good.
Yeah, that's good. But a question from Rebecca: if you use mixed dose, do you still need to apply Acron later? That's a practical one.
Yeah, that's good. Do you want to go, Charles?
It just depends on the environment, I suppose, and what else is going on. Might be best to go over a little bit more detail after this with you, Rebecca. But some cases is just the admixture will be used, and that will suffice. In other situations where there's, say, like a harsher, more corrosion, wastewater is a good example of that. We'll do both, and then when the spray on is included, that also from the beginning, that also acts as curing as well. So it's a really good way to ensure that is done, and there's QA to prove that curing as well. So yeah, if that helps.
Yep, very good. And Matteo says, what can be done to mitigate carbonation in concrete?
Yeah, that's a good topic there, Matteo. Matteo. With carbonation, you're really looking at the permeability of the concrete, and why that is when you CO2 by itself doesn't attack concrete per se. It's when it mixes with moisture and forms carbonic acid that it actually starts to break the microstructure of the concrete down. So really the best thing you can do against carbonation is to restrict that moisture entry at the surface of the concrete, or through that matrix of the concrete, because if you can stop that moisture, that acid from penetrating into the concrete, you restrict that attack really to the top surface. And yeah, obviously a We've tested hydrogels, the spray-ons there, and we're working on the admixtures as well, to a control versus a treated, and you can see the control is going in. I mean, it varies on the concrete, obviously, but typically it's double the amount of penetration into the concrete than we can get when you treat it with a hydrogel admixture or a spray applied. And with that, that doesn't just necessarily translate into double the service life, because it's not like slowing that down by half doesn't just translate to, say, 50 years to 100 years. There's obviously lots of other things that go into it, but it does give you an indication of how much more service life you can get out of that concrete. That's just on that too. You can either protect the structure right from day one with an admixture, or there's many spray applied treatments that can be applied down the track just to stop that moisture ingress there.
Awesome. That's good. So anything else, Brendan?
I've just come in at the moment. Looks like that might be it. No, hang on, we've got somebody typing. Just a moment. Would silane siloxane treatment do something against carbonation?
Yes, that's in essence in principle it does. So your a silane siloxane is forming a barrier on the surface of the concrete, and that's stopping the moisture getting into the concrete. That's only effective if it's done right from the very start of the project. Once you've got that carbonation inside the concrete, if it's approaching the steel, that silane's not really doing much for that front. In fact, when you're putting a coating on like that, and you've got moisture in the concrete, it actually excites the molecules and can move them around faster than if you did nothing. So I would strongly suggest to look at something like the penetrating hydrogel treatments that penetrate into the concrete and pass that first layer reinforcing steel and stop that moisture transmission in that critical cover zone there. So yeah, did would you say anything else to say on that, Charles?
No, I was just going to say in some cases where there might be a requirement for something on the surface like that, the hydrogel is still used as a backup, really, extra insurance for when there is a pinhole or a large failure, meaning the underneath isn't totally susceptible to attack. So it just really depends.
Yeah, and it's the same kind of idea with a silane. Essentially as a coating, they do penetrate in a little bit further than a coating, but yeah, again, very good if you can get it on day one, but once you've got that damage manifesting, you do really need to look at what you can do to that internal matrix of the concrete, and optimizing your mix design, admixtures, everything from day one I would say have more impact on that carbonation attack than applying a paint coating to the surface of that structure. Because I mean, I don't want to dive too deep in here, but the coatings also have replacement or service lives as well, and that's often a lot shorter. It might be 5, might be 10 years over against a 50-year design life. So you really want to have something. Have a mixed design that, or have thought about the durability to last for that 50 years without having to do anything major or replenishment, coatings, repairs, that type of thing. Trust that's helpful.
It's about preventing it from getting going in the first place, rather than stopping it with a barrier for when it does come through. So, yeah, excellent. If there's any other questions, we can happy to fire back. We can do it via email afterwards, or reach out to either of us. I'd be glad to help.
That's good. The ones that have come in have been very good indeed. Much appreciated. And yeah, as Charles says, we'd be very pleased to collaborate. If there's anybody's got any projects or project questions or general questions that you're coming up with all the time, we'd be happy to chat to you about it. Thank you very much, everybody, for joining us today. Great to have your company. Great to have the questions, the interaction. Thanks, Charles and Doug.
Thanks very much.
Awesome. Thanks, guys.
MARKHAM, adding life to concrete.